Hey everyone, I'm Scott Anderson, a technical writer here at InfluxData. Welcome to Influx Days, the virtual event. I hope you're enjoying it so far, and I'm glad you decided to watch or listen or just participate in my presentation today. Today I'm going to talk about map and reduce, two transformations that allow you to build really powerful custom Flux functions. So disclaimer, there's been some confusion about the title of this presentation. This is not about Hadoop MapReduce-like functionality in Flux. This is about two functions or transformations that you use to build powerful custom Flux transformations. I also assume in this presentation that you have at least a basic knowledge of Flux. If you don't, if you're just coming into it, I highly recommend watching this Introduction to Flux training that's hosted on Vimeo. This is one I did that walks through just foundational concepts of how Flux works, what it is, how it came about. Highly recommend watching that if you're brand new to Flux. A lot of what we're going to talk about is intermediate to advanced Flux concepts. You don't necessarily need that foundation of Flux, but it will definitely help to understand today's presentation. So to give you a quick background on what Flux is and how it came about, Flux is a functional data scripting language that lets you query, process, and write an alert on data in a single syntax. Typically, each step of this data workflow would be done in a separate syntax. You would query data with a language like SQL or InfluxQL or whatever database-specific query language you're using. You would then export that data and process it using some other syntax like process or Python or R, languages specifically built to work with and process data. You'd then use another syntax or that same syntax to write back to the database, and then you could use an entirely different syntax to process and alert that data. So one of the primary goals of Flux was to unify the entire data workflow into a single syntax. As we set out to design Flux, it has to be Turing complete, which it almost is. There's just a few things left to make it Turing complete. It had to be usable, had to be readable, flexible, extensible, testable, contributable, and shareable. Today, we're going to focus on the extensibility of Flux and really tailoring it to your needs and creating functionality that may not currently exist in the Flux language. We'll also touch on the testability, contributability, and the shareability of the Flux language as well. So the reason that extensibility was such it was one of the core goals of designing this new query or scripting language is because, excuse me, InfluxQL, the query language that you use to query data from InfluxDB 1.x, is really hard to extend. Anytime we needed to make changes to the InfluxQL language, it felt like we had to rip up the foundation of what InfluxQL was, make the modifications that we need, and then do that same thing over again the next time we needed to add functionality to InfluxQL. We also have TickScript, which is a language designed to work with capacitor and process and alert on data. TickScript itself is easier to extend, but to really customize the functionality of the language, it depends on external languages and user-defined functions, which essentially offloads processing into an external script or an external process. So the early strategy as we've been building out Flux has been to create primitive functions that can be used to create other functions. We've also recently introduced architecture to contribute to and distribute contributed packages. This is only in its infancy, but it's just within the last couple of weeks we've introduced this functionality. So custom functions. This is honestly one of my favorite things to do in Flux is to build things that don't exist. I am able to do things with Flux that I could never do with InfluxQL or SQL. So when it comes to defining a custom function, the syntax is pretty basic. And if you're familiar with JavaScript at all, this will seem really familiar to you as well. But essentially you define the function name, you then define a set of parameters and defaults if they have them, and then you define the function operations. So for example, let's say I want to create a square function that takes x and multiplies it by itself. I would name my function square, I would have an x parameter, and then my function operation simply multiplies x by itself. So one of the things that I take full responsibility for is in the current Flux documentation, it doesn't make this very clear, but there's a misnomer. When we talk about functions and transformations, and you've probably heard me mention the word transformations so far, a transformation is it's like a function, except it takes an input stream of tables and outputs a modified stream of tables, where a function takes a static value and outputs a static value. So I'm guilty of using function and transformation interchangeably, but they really are different, and the distinction between the two is fairly important. So map and reduce, the two transformations that we're going to talk about today, are actually used to create powerful transformations. Custom transformations that take an input set of tables, modify it in some way, and output a new stream of tables. So the definition or defining a transformation is the same as defining a function. You have the transformation name, you have the parameters, but there is always at least one parameter that represents a stream of tables being input into the transformation. This can be named anything. It could be T, it could be S, it could be foo, it can be anything you want. I use oh, I've just lost the word for it. I use just the convention of the tables parameter to represent the input tables. The left arrow operator, or the the less than sign with the hyphen, represents any data that is pipe forwarded into the transformation. I then take that set of input tables and operate on them in some way. So to illustrate the difference between a function and a transformation in the code, this is a primitive that exists in the Flux language, bool. It takes a value and converts it to a Boolean value. Again, the input is static and the output is static. But I could build a transformation that takes an input stream of tables and converts all the values of the value column to Boolean values. So I would create this custom transformation called toBool, which takes the input tables, uses the map transformation to convert the value in the value column to a Boolean value. Notice that this operation uses the bool function to operate on each row in the input tables. Both of these transformations actually already exist in Flux, both the bool function and the toBool transformation. In an actual query, it would look like this. I would have my basic query of a from, range, and filter, and then I would use my toBool transformation to convert all of my values to Boolean values. So again, the two transformations that we're really going to focus on today are map and reduce, and these are both really similar, but very different in important ways. The two ways that the ways that they are similar, or the things that they have in common, is they are both row iterators, meaning as you input tables into them, they will iterate over each row, modify them in some way, and then move on. So we're going to talk about map first. What map does is it takes an input stream of tables. And just to simplify this, we're going to look at one table in this stream of tables. If you're wondering why the input stream of tables has multiple tables, again, go back and watch the Introduction to Flux video that I linked to at the beginning of this. It'll explain it in detail. But I want to look at this one table. So again, map is a row iterator. It operates on a row one at a time. So let's look at this single row. So as map is iterating through the rows, each row that it looks at or operates on, it sees as a record. A A record is similar to like a JavaScript object or a Go map. It's a collection of key value pairs, where in this case, all the keys represent the column labels and all the values are the column values. So the map transformation expects an fn parameter. What the fn parameter is a function that operates on the input record. R represents the input record or the row record. So if I look at the row that we extracted from that table, I have all of the key value pairs representing each column. I then can use those values in the R record to build or remap a new row. I use dot notation to reference key value pairs in the row record. So in this case, I'm saying I take my row record, I input it into and remap this record where the underscore value key is equal to the R dot underscore value. This essentially remaps the value column to itself, so it doesn't really do anything except, it doesn't really do anything. But let's say I want to take my Celsius temperature that I have in this record and I want to convert it to Fahrenheit. And I want to update the field because the input field is temp C. I want to change the field to temp F. So I would use a map transformation to redefine the row record. I want to have the field key be temp F, and then I want to change the value to Fahrenheit by multiplying the existing Celsius value, R dot underscore value, times 9, divided by 5, and then add 32. So this will output a new row record with a field key and a value key, each with their values. When this gets parsed into a table, it looks like this. And you're probably wondering, wait a second, what happened to the other columns in the table? What happened to my time and my sensor ID? They were dropped because map, it remapped the row record with the explicit keys that we provided for it. This is where the with operator is really important when you're using the map transformation. That's this one right here. The with operator extends the row record. So as you define keys in the map operation, if those keys already exist, it will overwrite those keys. But if they don't exist, it will add the keys to the row record, and it preserves all of the other key value pairs in the row record. So using the with operator, my output record will include the time column, will include the sensor ID column, but my field column and my value column will both be updated to represent the values that were remapped in my map operation. When parsed into a table, it looks like something that we would expect. We maintain the time column, we maintain any tags. In this case, we have sensor ID, and the field is updated and the value is updated. So let's look at the table as a whole and how I would use this mapper operation. Let's say that this is my input table. I then pipe forward this input table into my map transformation where I'm converting it to a Fahrenheit temperature and updating the field. The output table will look like this. I'll have each row updated to represent the corresponding input row after it's been through this transformation that we define in the map transformation. So let's say I want to encapsulate this conversion of Celsius to Fahrenheit into a custom transformation. I'll call it 2F. I'll define parameters necessary to run the transformation, run the operation. In this case, I just need input tables. So I'll have my tables parameter that defaults to any data that is pipe forwarded into the transformation. I then take my input tables and I remap the row record using the transformation that we talked about before. I am redefining the field, it's now temp F, and then I'm converting the value, the temperature, the Celsius temperature value to a Fahrenheit value. So looking at the same operation before, I have the input tables, I have this long, verbose map transformation. Once I define that custom transformation, I can simply use the custom transformation to get the same output. So what if I wanted to convert temperatures to text based on a range? So for example, any temperature below 0 degrees Celsius, I want to add freezing to, which is a simple human readable text temperature. 0 to 15.5 is cold, 15.5 to 26.5 is mild, etc. This is where you can actually use conditional logic when mapping key value pairs inside of a map function, the fin function inside of a map transformation. So the syntax is pretty simple. You have your column key, and then you begin this if-else loop of defining the value for that key value pair. If r._value is equal to foo, then return bar, else return bas. So let's say I create this custom transformation called temp to text. I have my input tables that I'm then pipe forwarding into a map transformation. I'm using the with operator to retain any rows or columns that exist in the input tables. I then want to add a temp_text column with the human readable value. This is where I'll start to build in the conditional if-else logic. So as I build out these ranges, if r._value is greater than or equal to, or excuse me, less than or equal to 0, then return freezing. Else if it's greater than 0 or less than or equal to 15.5, return cold. Go through all of the different ranges. And then I also need to provide a default. In case none of these expressions resolve as true, I need to provide some type of reasonable default. In this case, you should never have a value that resolves as, or that doesn't resolve as true. So you should never get unknown. The only case that this might be true is if there's a null value somewhere in your tables. One thing to note also is just as in other functional languages and conditional loops like this, once an expression resolves as true, it returns the then value, and it doesn't read it doesn't evaluate any of the remaining expressions. So if my value is less than or equal to 0, it stops there, and it doesn't evaluate any of the other expressions. This becomes important when you start to build the order in which values are evaluated in your conditional expressions. So if I take my custom temp to text transformation and I use this input table, I have a negative Celsius temperature and then other Celsius temperatures. This will be my output table. Because I used the with operator, it didn't modify any of the existing column values, and I only added the temp_text column with the corresponding text value based on the conditional logic inside my map transformation. So I get freezing, mild, and hot with the corresponding temperatures. So some example custom functions or custom transformations using map. These are some basic mathematical operations. Multiply by x, it takes input tables and it multiplies all of the values in the input table by x. So this will just return the same input table with a modified _value column where all of the values in that column are multiplied by x. Square does the same thing that we had shown before, where it takes the input tables, multiplies the values in the value column by themselves, and returns a table with those values. Quarter takes the value column and divides by 4, so it returns an output set of tables with all the values divided by 4. Here's some other mathematical operations. Flux ships with a math package, which provides some really powerful primitive math functions to create some, potentially create some really powerful mathematical transformations. So just as some quick examples, let's say I want a sign transformation that takes all my input tables and returns the sign of the value in the value column. Or I can use constants inside the math package. So for example, in circumference, I need the constant pi, which is included in the math package. So to calculate the circumference assuming that my value column contains the radiuses or the radii of, those values are what are in the table. I would then multiply the values. I'd use the formula 2 pi r to calculate the circumference. So I use the math.pi constant to represent pi in that formula. Same with circular area. I have my map transformation that I then use the formula pi r squared to calculate the area of a circle. I use the math.pi constant and multiply the existing, or I square the existing values. You can also do some pretty powerful string manipulation using map. And these are just some examples, but they use the strings package, which is full of functions that both evaluate and modify string values. For example, if I want to remove a host prefix from my input tables, let's assume that I have a host column, that all the values in that column have a host underscore prefix. To remove that, I would use the strings.trimPrefix function. I would input the r.host value, and I would remove the prefix host underscore. Let's say I have a bunch of tag values that I want to replace the spaces with them with a given character. In this replace spaces transformation, I take my input tables and I have a character parameter with a default of underscore. What this character parameter is used for is to replace all the spaces in the values in the value column. So I use the strings replace all function. I pass in the r.underscore value column value. I search for any spaces in that value, and then I replace them using the car or character parameter. Let's say I want to create a human readable message based off of values in the value column. This human readable message transformation creates a new column called human readable, and I use Flux string interpolation to build a new string that says the current value is whatever the value in that row is. So there's some common gotchas that you need to know about whenever you're using map. The first one, just remember the with operator is your friend. Almost always you'll want to preserve any existing columns in your input tables. It's pretty rare that you don't. There are use cases for it, absolutely, but the vast majority of cases, you'll want to use the with operator to extend your row record rather than completely redefining the row record. Anytime you're doing mathematical operations using map, the two operands, or more, I guess you could have more than two operands, but all the operands must be of the same data type. So you can't multiply an integer by a float, you can't concatenate an integer and a string, etc. Map does not add new columns to the group keys. And if you don't know what group keys are, just a quick summation is they define how tables in an input and output stream are grouped. Again, that introduction to Flux walks through how group keys work. But essentially it's a list of columns for which all tables or all rows in a stream have the same value. So when you add a column using map, it does not get added to the group key. So your output tables will not be grouped by the newly mapped values. To group by those values, you have to explicitly use the group function to group by the new column. Map only operates on a single row at a time, and there's a couple of repercussions with this limitation. Number one, you can't use values from previous or subsequent rows. So you can't do like a cumulative sum where it updates the current row value using the sum from the last row and preserve all the rows. It can't do that. It can only use the values that exist in the current row record. This also means that if you want to, let's say for example, you want to use two different field values in your map operation, to use those values, you have to make sure that they exist on a single row. And you can use pivot or join to do this. And my preference is pivot, but it doesn't work in all situations. But the gist is you need to get those values in a single row to be able to operate on them. So let's talk about reduce. Reduce is very similar to map, but very different in a key way. So let's look at this input stream of tables. Reduce is what we call an aggregate transformation. What all aggregates do is they take an input stream of tables. In this case, again, we have reduce. And any other aggregate transformation like mean or sum or count, they all do this. They take an input stream of tables. Each table has multiple rows. They reduce each of the input tables into a corresponding output table with a single row. And that single row represents an aggregate value of all the rows in the input table. So for example, if you were to use the mean function, each row in the output table would represent the average of all the rows of the corresponding input table. So what reduce is it allows you to create custom aggregate transformations. So let's look at a single table from this stream of tables. Again, it's the same data that we had before of our Celsius temperature. When I reduce this down, I get this table returned. I still have my tag, I still have my field, my value has been updated, but you'll notice that I lost the time column, and we'll talk about why here in just a sec. So the reduce transformation expects two parameters. The first one is fn. This is a function that takes in the row record as well as an accumulator record. What the accumulator is it's a record output from the previous row iteration. This fn function actually builds a new record that then gets reused in the next iteration on the next row. The identity represents the initial state of the accumulator, because when you operate on that first row, there's no previous iteration to use, so it requires a default value, and that's where identity comes in. So if I look at this input table, I see that I have a time, a field, and a value column, and the group key of this table is field, and that's important, and I'll explain why in just a minute. But as reduce operates on this table, it iterates through each row, just like map does. And each row, as it reads each row, it reads a record, so you have all the key value pairs representing the column in the row. So as I look at my fn parameter, in this case, let's say I want to do a custom sum function. You don't need to. The sum function or sum transformation already exists in Flux, but just for the sake of demonstration, we're going to create a custom sum transformation. I would take the current value in the current row and I would add it to the sum in my accumulator record. And then I would define the identity as sum is 0. Now the important thing to point out here is that the output record of the fn function must match the structure of the identity because the identity and the accumulator, because that record gets passed into the next row iteration as the accumulator. So those records have to match in structure. So for this first row iteration, because there's no previous iteration, my accumulator is equal to my identity. So I have sum is 0.0. So the return record is going to include the sum key, which represents the value of the current row plus my accumulator.sum, which in this case is the identity. Let's expand these variables down until ultimately this is the return record that I get from this iteration of this first row. This return record then gets passed in as the accumulator of the next row iteration. So in the next row, I have my sum, I have my value of the current row, which is 12.2, plus the sum that's in my accumulator. So 12.2 plus 1.3, which resolves to 13.5. And that gets passed in as the accumulator in the next row iteration, which returns a new record, which then gets passed in as the accumulator to the next row iteration until it finishes iterating through the entire table. So when we get to the last row, we have this final accumulator value. In this case, its sum is 37.4. This represents the sum of all the values in the input table. When building the output table, Flux does a few things. It includes columns, or it parses the table based off the final accumulator. So we'll include a sum column with the sum value. But it will also include columns in the group key. So in this case, it will have an underscore field column. But then it drops other columns. Now, if you think about this, this makes sense. Because in a table, all columns in the group key, or every value for that column, will be the same in that table. If the values are not the same, and you don't define how to aggregate those values or how to reduce those values in the reduce operation, Flux doesn't know what to do with them. So it just drops the column. So in this case, we'll actually lose the time column because Flux doesn't know how to aggregate the time column. So the return table is the field example with the sum value returned from the sum operation. So if we look at a table that more accurately represents what you would see when querying InfluxDB, you would return, it would include a start column, a stop column, a time column, a measurement column, any tags, a field, and a value. So using the same example sum transformation, I would take this input table and I would get the following output table. I retain my start, I retain my stop, I retain my measurement, my tag, my field, and then my value is updated. Now you can do things here. Let's say you want to add the time back in. You can actually duplicate the start or the stop column to represent the time of that aggregate value. So if I have multiple tables, these two tables are differentiated by their different tag values, but their group keys are the same. If I pipe forward these into that same transformation, these are the output tables that I'll get. Two output tables differentiated by tag, but their values represent the sum of all the values in the corresponding input tables. Let's say I want to create a custom average transformation. Again, you don't need to because the mean transformation already exists in Flux. But just for the sake of demonstration, let's look at how you would create a custom average transformation. I take my input tables, I would then pipe forward my input tables into a reduced transformation. But to calculate an average, we first need a sum. So as I define my fin function in my reduce operation, or my reduce transformation, my sum is going to represent the value of the current row plus the sum of the included in the accumulator. Also, to calculate an average, you need a count. So in this case, I'm taking the accumulator.count and adding 1. So this increments through each iteration through a table. So each row will add 1 to the accumulator count. I then need to calculate the average. The average is my r._value plus the accumulator.sum divided by my accumulator count. Now, the important thing to understand here is that sum and count, the sum and count calculated in this iteration cannot be used in this current iteration. You can only use values in the existing row record or values in the accumulator generated from the previous iteration. So the sum and count values calculated here will actually only be used in the next row iteration. So that's why in my average, I have to recalculate the current record sum and divide it by the accumulator count. Now the accumulator count at this point hasn't been incremented because again, we're using the accumulator from the previous iteration. So it's dividing by the count up to this row. My identity, again, it has to match the structure of the record that gets output from the fin function. So I have sum starts at 0. I want to start my count at 1 because on this first row iteration, if I try to divide by 0, it will fail. And then I also pass on the average that gets generated from this iteration. So I need to provide a starting average, which is 0. So using this custom average transformation, again, let's look at this input table. It's the same table we used before with the group key of field. I would have this, in this first row iteration, R would equal this record with time, field, and value. And then my accumulator for this first row iteration would represent, or is populated by the identity defined in my transformation. So this returns a record with sum, count, and average. As I expand these values, this is the return record that then gets passed into the next row iteration. We just go through each row, expand these values down, and ultimately, this is the final accumulator that gets output. When this gets parsed into a table, I have my field, I have my sum, I have my count, and I have my average. Now, I don't necessarily need the sum and the count in my output. So typically what I'll do in these cases is I'll actually drop my sum and count columns because I no longer need them. And then I'll actually change my average column to be the underscore value column, since that's what InfluxDB and Flux recognizes the value of a field. So if I take two input tables, I pipe forward them into my custom average function. These are the tables that will get returned, differentiated by tag. I maintain my field, and then each of the values represents the values of the averages of all the values in the corresponding input tables. Again, I dropped the sum and the count column, so they aren't included in the output columns, and I renamed the average column to value. So some example custom transformations or functions using reduce. This is one we get a lot of requests for, min, max, and mean. This takes the input tables, pipe forwards them into a reduce transformation. In my identity, to create or to determine the min, max, and mean, I need to compare the values using conditional logic. But I also, because I need to know if this is the first iteration of a reduce, because if it's, as you look at where min is defined, if accumulator.count is equal to 0, then the minimum value is whatever the value is in the current row record. Else, if the value is less than the accumulator min, then replace the min value with the current record value, or else maintain the accumulator.min. Same with max. If this is the first iteration, then use r._value as the max. If it's not the first iteration, and the r._value is greater than the accumulator max, then set max to the current row value. Or if it doesn't meet either of those, return max. So in my identity, I am using the count as an index, essentially, where I'm counting the number of iterations, and I just need to know if it's the first iteration so I can default to the min and the max. I also use count to calculate the mean. So in this case, because count starts with 0, I need to be sure, in order to get this to not fail on the first iteration, in the mean calculation, I actually have to add 1 to the accumulator count. So in my mean definition, if the current count is equal to 0, then the mean is the current row value. Else, I need to calculate the sum and divide that by the count, which I have to explicitly define in this calculation as the current accumulator count plus 1. I also cast that to a float because my numerator is going to be a float, and in any mathematical operation, the two operands have to be the same data type. Another custom transformation using reduce is candlestick. And if you don't know what a candlestick is, it's used to generate these type of graphs. They're typically used in financial, or to visualize financial data. They represent the min, max, and the opening and closing stock prices within a trading period. Generally, they can be used for other things as well. But to do that, I again need to calculate the first value in a table. I need to calculate the last value in a table, and then the max and the min values in that table. To calculate the first, I need to track the index, or just the iteration count as it goes through. So in my identity, I have the index starting at 0, and then all my first, last, max, and min values starting at 0. As it iterates through each row, I take my accumulator index and increment it by 1. And then in my first value, if the accumulator index is 0, I know it's the first iteration, and I can just set it to the r._value. And then through every other iteration, it'll just default to accumulator.first. So we'll always retain that first value. With last, I can just set it to the current row value, because it will just update the last value for every row that it iterates through. And then after the final output, it'll just use the value from the last row that it processed. Max, I'm comparing the current row value to the accumulator max. If it's greater than, I set it to the row value. If it's less than, I set it as or I retain the accumulator max. Same with min, just the opposite logic. I then drop the index column after we perform this reduce operation, because I don't need the index. I only want the first, last, min, and max columns returned. Another thing you can do with reduce is manipulate strings. So in this case, let's say I want to create a comma-separated list of all the values in my value column. I can take my input tables, pipe forward them into a reduce transformation, and I'm taking and using Flux string interpolation to take the existing value in the current row record, convert it to a string, and then add a comma on the end of it. The only catch here is the final output is going to have a comma on the end of it that I don't necessarily want. So I'm using map to go over that row, and I use the strings.trimRight transformation or function to remove that last comma from the comma separated list. So again, some common gotchas with reduce. Reduce does not support the with operator. If the column is not in the group key, and if it's not explicitly aggregated in the reduce operation, it just gets dropped. Again, columns not in the group key or explicitly mapped will always get dropped. Mathematical operands must be of the same data type. And reduce is destructive, and it will only output a single row per table. So while reduce does carry data from one row to the next, it removes the previous row. It will only ever return a single row table. So now that you can create these really powerful custom transformations, let's contribute them and share them with the Flux community. And again, we've just laid down the foundations of creating a contribution system to Flux, and this is just the first iteration. Ultimately, the goal is to create a hosted repository of custom Flux packages contributed by the community that you can then import into your Flux scripts and use. This is that, but not quite as freeform as we intend it to be in the future. So the steps to contributing to Flux: 1, fork and clone the Flux repo at github.com/influxdata/flux. Navigate inside of the Flux directory to the standard lib contrib directory. This is a directory that houses user contributed packages. Create a new directory using your GitHub username so that all of your packages are namespaced to your GitHub user. So in my case, I would create a directory at Flux standard lib contrib Sanderson. That's my GitHub username. I would then create directories for each subpackage. Technically, you can actually just turn your user namespace into a package, but I generally create sets of functions or transformations specific to a use case. So for example, if I have a set of transformations and functions that all have to do with finance, I would create a custom finance package. So I'd create a directory, Flux, standard lib, contrib, Sanderson, finance. I would then add a package definition file. What this looks like, or excuse me, this would be inside of the package directory. It would just be the package name.flux. So in this package or this finance.flux, I would first declare the package name, so package finance. I would then import any dependencies that this custom package requires, so math and the math package and the regexp package. I can also define options for my package. This is a little known feature of Flux that packages can have options. I won't go into detail about them now, but they do exist, and they aren't documented in the public-facing Flux documentation, but they are in the engineering documentation or the source code documentation for Flux. I can then define constants to include in my package. So for example, let's say I want an array of all the tickers for the New York Stock Exchange to be included as a constant inside of my custom package. I can do that. I then define all the custom functions and custom transformations inside of my package with comments explaining what each of those do. This is a really basic package definition file. So with that package definition and each of those custom functions, I would then need to add tests for each function. And I could do an entire presentation on tests, so I'm not going to go into too much detail. It's going to be a really quick overview. But essentially, you have to create a test, a single test file for each function. You can't test multiple functions or transformations in a single file. So in this case, I want to create a test for my retire in transformation. It would just be retire in underscore test.flux. And this is what the test file would look like. I define a package name with underscore test. I import both the testing package and my custom package, which is contrib Sanderson finance. I then define indata, which is annotated CSV that represents data that gets input into the transformation in the test. I then define outdata, which is also annotated CSV, and this is what the data should look like after its output from the custom transformation. I then define a test transformation that represents my custom transformation, and then use the test framework that is included in the testing package that compares the input of my transformation to the output of my transformation. And if the two match, the tests pass. If the two fail, or the two don't match, the tests fail. Really, it seems complicated, but it's pretty simple in principle. So after you've added your tests, you need to generate the standard library. There are some dependencies to do this. You need Go, you need Rust, and there might be a few others, I can't remember. But once you have the dependencies, and the dependencies are all documented inside of the Flux repository, you can either use make or Go generate to generate the standard library. You push your changes to GitHub, submit a pull request on the Flux repo, and once that pull request is accepted and merged, and a new version of Flux is cut that includes your custom package, you can then use your contributed package, and using it is really simple. In any Flux script, you would import your custom package. So in my case, it would be contrib Sanderson finance. You would have a basic query that uses the from function, the range, and the filter transformation to return a set of data. And in this case, I'm going to use my retire in custom function. The package reference always uses the last directory name in the package directory path. So I would do finance.retirein and then set my goal. Now that you can use your contributed package, you can share it with the world. There's multiple ways to share it. You can, again, the package will be on GitHub inside of the Flux repository. You can contribute to the Flux documentation. You can share it on social media, but let the world know that you've created functionality that works for you, because guaranteed there's somebody else out there that's looking for it as well. Thank you for your time. I hope you've learned a lot about using map and reduce to create powerful custom transformations. If you have any questions, if you want to pick my brain, you can reach out to me. I'm more than happy to answer any questions that you have. This is my contact information. I'm in the InfluxData community. I'm in the community Slack as well. Feel free to reach out. I hope you have had a great experience here at Influx Days, the digital edition, and continue to have a great experience. And again, let me know if you have any questions. Thanks so much.